All right. All right. So let me try to share. All right. All right. Share. Right. Okay. So can you all? I assume you can you all see this?
I can.
Yeah, in the chat. Right. All right. Yeah. Okay. All right, fellows. So as I said, I'm recording this already. So yeah, the idea today is to talk about cryptography on elliptic curves. So in some ways, the concepts are not really new as such. We're gonna talk about public key crypto systems and digital signatures. The only real difference is that we're going to be using analogs of El Gamal, really, but working on the group of an elliptic curve. So, all right. Um, right, okay, so let's go to the elliptic curve version of Diffie-Hellman. Remember that Diffie-Hellman is a way of sharing a secret in a way that only two parties know the secret, but no one else does. Here, what you're gonna be sharing as a secret is a point on an elliptic curve, right? So in terms of the public information, we're gonna have an elliptic curve which is public over a finite field Fp, where the prime P is public. And of course, we're looking at primes with, very large primes with hundreds of digits even. And one other ingredient, again, all of this is going to be based on the difficulty of discrete logarithms on elliptic curves. So one of the other ingredients is a point on the curve. And the order of this point should be rough, right? So at the very least, the order of this point on the curve should be divisible by a very, very large prime. In fact, potentially it could actually be equal to a prime, but that's usually not that easy to achieve. Um, Let me remind you that even this, there's a little bit in this about how would one choose an elliptic curve that to begin admits some cyclid subgroup of large order, of large rough order. And we can get to that a little bit later. But let's assume that you can do that. So the whole exchange is going to depend on having a point of large rough order. The private parameters that Alice only knows a parameter which is gonna be, she's gonna use it as a secret exponent. So it's a number less than or equal to the order of the point P, and also Bob chooses a secret. So these can be chosen randomly and independently, obviously, of each other. They are only known to Alice and Bob, respectively, right? Um, and so the way you get the corresponding public information from this um, is by exponentiating, right? So you take the Alice secret as an exponent slash multiple, right? Since we're additively. So this is the n-fold multiple of p plus p plus p, n a times whatever that is. So that exponentiated point, so this is kind of like the exponentiated version of Alice's secret, and it is safe to send that, make it public. Again, assuming the untractability of discrete logarithms. And correspondingly, the public component of the public information of Bob is obtained with Bob's secret, exponentiating p with that exponent, and then you get a point which becomes Bob's public information. So the public information of Alice goes to Bob, and that of Bob goes to Alice. And this could be happening when, with everyone, like a mailman, being able to see the public information. That's okay. And then the private computations behind this are exactly the same way that it was done in the Diffie-Hellman exchange on other groups. So you take, what Alice does is she takes her secret as an exponent of Bob's public information, and Bob takes his secret as an exponent for Alice's public point, right? And the shared secret is equal to these two, right? Because this quantity here, Na times QB, is actually Na times NBP, correct? Since QB is NBP, but that is the same as NB and AP, just by commutativity of multiplication. And this part here, NAP, is Alice's public key, right? So that's why NAQB and ABQA are both the same piece of information, and that is the shared secret, which is an elliptic, a point on this elliptic curve, right? So really, formally, this is identical to Diffie-Hellman key exchange on, when we're doing it in modular arithmetic. So are there any questions about this? It's really the same thing. So if there's any questions, feel free to ask, but you tell me. No? All right, so I'm really hoping that it is because you already are familiar with Diffie-Hellman, and there's really no new concepts to absorb here. Hopefully, it's really the same. So let's do, just a little example, whatever. As I said, there's a little bit of a question of how one actually would choose the curve so that you can get a point with the right characteristics. But here I just took a curve, right? Which is actually a curve over the rationals, right? But I'm considering this as an equation over FP. And here I'm being really sneaky in that I chose P in such a way that the order of the elliptic curve over FP is pretty large. Let me remind you that by Haas's theorem, the group underlying an elliptic curve modulo P has roughly P points, P plus minus an error of the size basically root of P or 2 root of P at most, right? Just so you see, this is actually equal to P plus 1 minus an error, 62, which is much smaller than P, right? And I just chose P in such a sneaky way that this order is, so there's actually an element that generates the whole group. So it turns out that the point 2, 1, which 2, 1 is a point on this curve, already has that order, 3790. Right? I mean, this is not particularly rough, but whatever. I mean, given that we're dealing with primes of 4 digits, the fact that there's a 3-digit prime dividing this public point, it's good enough, I guess, for our purposes. So, so here I just, for the sake of argument, I take Alice's secret to be 314, which when you multiply 314 by the point P, and again, I emphasize once more that the multiplication 314 times 2, 1 should be done using a fast exponentiation, or in other words, the double and add algorithm. And that if you were doing this over the rationals, you would be getting potentially horrendously complicated points on the curve. But because you're doing everything modulo P, you never have to deal with numbers larger than 3851, right? And when you do that, you get the secret 314 times P modulo the prime 3851. You just get this very manageable shared secret for this is I'm sorry, this is the shared of Alice's secret, but this is public, right? And by the same token, I guess Bob's secret is 777, and you multiply 77 by 21 mod p, and you get the public information of Bob is this point. And it just turns out that if you take Bob's point and you multiply it by Alice's secret 314, you get whatever 35, 23, 32, 10, and that's exactly the same as if you multiply 777, which is Bob's secret, by the public information from Alice. So you get this, and whatever. And as way of a check, this also gives me a tiny bit of an excuse to remind you how exponentiation works. So both of these should be equal to 314 times 777 times the point P, correct? So if you do 314, which is one of the secrets, times 777, the other secret, times the point P, it is 243,978 P. But, and this is the bit that I just want to remind you, because P has order 3790, you don't actually have to multiply P by 243,000 and change, because the powers of P repeat every 3790. So if you reduce the exponent 243,978 modulo the order of P, you get 1418, and that 1418 P is also the shared secret. So it works exactly as you would expect, and as I said, there's really no conceptual difference, just the context of elliptic curves versus what you did in Diffie-Hellman earlier in residue ring Z mod n. So we good? Think okay? Oh, I'm sorry, there was a question here in the chat that I didn't see. Sage multiplication, use double and add. Okay, so yeah, so John is asking if Sage multiplication does double and add. The answer is I don't actually know, literally don't actually know how it's done, but I suspect that it is essentially double and add. So it has to be fast exponentiation, perhaps with some improvements. Let me remind you that last time we talked about double and either add or subtract, because subtraction of points on an elliptic curve is the same as addition, except for changing the sign of the y coordinate, which is a really inexpensive operation. So in reality, the multiplication or the exponentiation of points on elliptic curves is done with a fast algorithm, and it is likely some kind of variation of double and add. It is probably double and add or subtract. Or it may be something slightly more clever than that, but nothing fundamentally different, because roughly speaking, the fast exponentiation is roughly speaking the best that is known for elliptic curves, except for that little twist of maybe double add and subtract. Yeah, so that's the extent of my knowledge. And if you want, maybe if either you or I may be curious and look at the code for the operation on elliptic curves and see how it's actually implemented. I mean, you know that one of the advantages of Sage is that it's open source, so you can actually go and look at how it's done. In fact, if I'm curious enough that I'll probably go and see, but I'll be happy to give you a little bit of extra credit in whatever homework, next week's homework, if you go and analyze the code and you tell me to the best of your understanding what is the way in which it is being done. So that's actually a very interesting question. Does that sound good? All right, John. So then let's move on. Now that we just finished with Diffie-Hellman, right? Now, the next thing that we do with exponentiation is the Diffie-Hellman public key crypto system. And, you know, except for some minor adaptations, the way this is done on elliptic curves mirrors closely the way this is done when we were working in ZModN. So let's start with the setup here. Not surprisingly, the setup is the same as for the Diffie-Hellman key exchange. Some elliptic curve over a finite field of P, let's say, where P is some large prime. And all of this is going to depend on the difficulty of discrete logarithms. So you need a base, a point P on the elliptic curve, which has large order, and that order should be rough. Perhaps a very large prime, or at least divisible for some large prime, right? And remember that the public key crypto system is asymmetric in that Alice shares some public information, but she keeps a secret, and everyone, in this case Bob, is able to send Alice information securely, right? So Alice chooses a secret which is less than it's actually an exponent. It's going to be used as an exponent of P. And so therefore, that secret, you can think of it as something defined modulo n. So some random exponent modulo n. And just as before in the key exchange, the public key of Alice is the exponentiated form of that exponent. So that exponent times P, where P is the point that we chose as generator of this large cyclic group, right? And this is published. So this is public information. And the plain texts that we're gonna send are actually points on elliptic curves. I will make a comment in a second, like, why on earth would anyone ever want to send a point on an elliptic curve as a message? We'll get to that later, but but anyway, so let's say that what Bob actually means to send Alice is a point on an elliptic curve, but he wants to do that secretly, right? And just as El Gamal earlier, what Bob does is choose a random exponent, so an exponent less than n. It's also going to be used as an exponent. And the first thing that Bob is going to do is compute the first part of the ciphertext is the exponentiated version of P, K times P for that random exponent, right? So that's the first piece of the information. And the second piece of this cipher system, right, is adding to the message M K times the Alice's public key, correct? So there's the two pieces. C1 is in a way of sending the random K, but encoded, and in other words exponentiated. And C2 is a masking of the message using that random piece of information and Alice's public key. So the decryption here is very simple, because, well, how on earth are you going to recover M? Well, obviously you would have to recover M from C2 by subtracting, correct? If from C2 you subtract K times QA, correct? That is obviously equal to M. But the thing is that KQA, because KQA is equal to K times NAP, that's NA times KP. So NAC1. So the way the decryption works is that you recover the secret by using Alice's secret. So Alice computes this using her secret and the two pieces of the ciphertext C1 and C2, right? So remember that El Gamal public key has this feature where in order to send a message, you have to send two pieces of information. So it kind of like doubles the amount of information you need to send, right? All right, so this is, again, very similar to the earlier situation with El Gamal. So are there any questions here? Yeah?
No questions.
Okay. All right. All right. So, okay, I guess now I'm gonna do some kind of mini example. Again, you know, my favorite elliptic curve, or at least the one I'm using for examples, is x cubed plus x minus 9 equals y squared over fp, where p is 3851 with the same point p, and the order of p we saw is 3790, you know. Now, Alice's secret is 3141. Right? It's less than the order. So just choose some kind of random thing. Now, of course, it's not very random because I like the number 314941. You probably can tell why. And her public key is obtained by multiplying this by the point p 2 comma 1. And when you do all of that modulo p, you get this 5372464, right? And let's just say that Bob wants to send the message to 718 comma something. Oh yes, and this is something I wanted to say earlier. So in the real world, why would you want to send a point on an elliptic curve? The answer is you really don't want to send points on an elliptic curve. But you can see here the first 4 digits of E, 2.718, you know, etc. So what the message that Bob actually meant to send Alice was 2718. And in this case, he was lucky enough that when you use this as the x coordinate, there is a corresponding y coordinate that makes this be a point on the elliptic curve, right? So that's one step, getting one step closer to real world, is that you're sending a point on an elliptic curve, but really only the first part of the point is kind of what is meaningful, right? And whatever, let's just say that in sending the message, Bob chooses the random number 1, 2, 3, 4. Again, not very random, right? And so the first part of the ciphertext is 1, 2, 3, 4 times p. So you get something. And the second part is adding to the message 1, 2, 3, 4 times the public key. And you get 33422257, which is not related to the message in any obvious way, of course. And in doing the decryption, you subtract from the second part, you have to subtract from C2, you have to subtract 1, 2, 3, 4 QA, but 1, 2, 3, 4 QA is equal to 3141 times C1. So you subtract from C2, 3141 C1, and you get the point that we started with, the message 27181170. Does that make sense? Questions?
It does, to me at least.
So if you notice what I was talking about, thanks, Michael. So if you notice what I was talking about, I said that the message that Bob actually meant to send Alice was 2718. Because we're doing this on elliptic curve, on elliptic curves, he kind of had to find the correct y to send this as a point. But what if 2718 did not correspond to the x coordinate of a point on the elliptic curve, right? We talked about it last time, that if you, so the cubic polynomial that appears in an elliptic curve is sort of a good mixer. So sort of like really like a very random number generator. It mixes the elements of FP quite well, right? So the chances that if you try to send a particular message like 2718, that it actually will correspond to the x-coordinate of a point on the curve are roughly 50%. A very, very, very close to 50% by Hasse. But what if it isn't? So what you do is you give yourself a few extra bits, let's say 10 extra bits of garbage that you can use any way you want. Let's just say that that you let's just say that you only wanted to send a message of 3 digits long, right? So let's just say we're, I don't know, whatever, working based like 2 to the 10, right? So you only allow yourself to send messages up to 10 bits. However, the points on the elliptic curve, I'm sorry, are up to like, almost 4,000. So you have at least one extra bit of leeway. So you could try to choose the leading bit of the number either as a 0 or as a 1, but choose to ignore it in the coding in such a way that if one of them doesn't work, then hopefully the other one does. So that is so the way encryption of messages is done on elliptic curves is probabilistic encoding. So normally you're not going to be able to encrypt with 100% probability, but if you give yourself a couple of different trials, and if things are done correctly, those trials are likely to be fairly independent of each other, then you have a very high probability of success. You may still end up in failure, but but if you have if you had 10 bits of leeway, then the chances that all of your examples would end up in a failure is, you know, 2 to the negative 1024. So it's just never going to happen, right? Right, roughly. So, but anyway, so that's kind of a side issue here. In that, how does this relate to actually sending real world messages? Um, all right. Um, are we? Are you all okay? I'm sorry. It sort of looked like I may have lost you all. Is what happened here?